that are coming into it, that sort of thing. So the design of the database is a very important part of the development of a system like this. So if you want to read more than what's in this lecture, there are some books that you might want to have a look at. Connolly and Begg and Date, both, you don't need to read both of them, you can read either of them, they have the same material, right? They're both fairly old books, so it should be easy to get second-hand copies if you want them, right? In second-hand bookshops around or online, and of course you can get them very cheap that way because they're old textbooks. People sell their old textbooks, you might get them for a few pennies, that sort of thing, right? So it's kind of nice. You know, there are newer versions of them. I think everything that you need is in these versions, so there isn't reason to fork out for the extra money. Unlike the Somerville one, which has been substantially updated to reflect the changes in software engineering practices, particularly Agile, the latest edition is definitely better than previous editions. These ones, not so much. Okay. In terms of looking at UML for databases, in both cases these are online articles or documents that you can just download for free. Okay, it's not worth having a book on those topics because UML for databases is still not concretely defined. Okay, so people use it, and we'll talk about how you use it in this lecture, but different people will use it in different ways. These two articles set out fairly standard ways of using it. So in today's lecture, first of all, briefly touch upon the evolution of databases. We'll talk about the relational data model, which is the foundation of modern day databases. Talk about the UML profile for databases, so how you would use UML to design them. The idea of entity relationship modeling. Traditional table normalization. Now this is the biggest part of database design, is this idea of normalization. So I'm going to spend a fair bit of time talking about it. I've also included at the end of the lecture slides an appendix, which I almost certainly won't have time to cover in this lecture, right? Those of you who've downloaded the lecture slides will notice there's something like 70 slides. In this way I can do that in 2 hours. But it's a supplementary material to what I'm doing in the lecture, slightly different way of explaining normalization because it is such an important concept. I thought it's important for you to see different ways that it can be presented. Okay, and then this idea of normal and pre-normal forms. Okay, so databases are generally dealing with business data of some form or another. Okay, it might be information about stocks, it might be information about customers, it might be information about the staff, about the business processes that are used, whatever, but they do contain business data. And it's extremely valuable because it's core to the business, okay? How you store your data and how accessible it is and the way that you can access it and see the patterns in it and that sort of thing can give you the edge in commercial operations, okay? If you find it easy to determine where the weaknesses in your sales are, for example, that's something that you can address explicitly. Whereas if those details are hidden because of the way that the data is being stored and you're not seeing the patterns in the sales it might be on a weekly basis or a monthly basis or an annual basis, or it might be because of things that happen at a particular time of year, you know, that type of thing. Being able to recognize those patterns can be very important. Unlike most software systems, the data tends to be persistent. Okay, so even when you upgrade your system and you replace it with completely new software, you usually want to keep the information from the previous iteration. Right? So that can involve using the database that was used before, or it can involve creating a new database and importing the data from it. But the data itself stays there. And it's not necessarily accessed by just one program either. It might have many, many different systems within the company that access the same database and use different bits of the information in different ways. And different users of the system are going to be using the data in different ways as well. And because of both of these things, because it's valuable data and there's lots of different people using the data in lots of different ways, it needs to be protected. It needs to be safe, even if the system fails, so you don't want a system crash to destroy your database. Or at the very worst case, if your system crash destroys the database, you need to have a backup, a recent backup of your database. And you need to ensure that only the right people access the right data within that database. So you don't want external users to be able to gain access, but you also don't want people within your company to get access to parts of the database that they shouldn't do. So everyone might be able to access the sales information, but a very restricted set of people should be able to access the employee payment section of the database. As an example. Okay, so the history of database systems. Well, in the early days, basically people used punch cards to store data, right? And we're talking about things like, in the same way that punch cards were used for programming computers, it was also the way to input data and to store data, so that the computers could punch holes in the card that would store information that could then be read back into the computer, right? In the 1950s, magnetic tape started to be used to replace punch cards. Okay, punch cards were still generally used for computer programs at that stage, but for actually storing and reading data, they started to use magnetic tape. Now, both of those things have physical characteristics that mean that the data was treated in particular ways. Most notably, it was a write once, read many type of system. Okay, once you've written the data, it wasn't modified. You could rewrite a magnetic tape, but when you rewrite a magnetic tape, basically you rewind the tape and you rewrite from the start. You can't rewrite a particular section of the tape unless the thing you're replacing it with is exactly the same size piece of data, right? Because otherwise, it's a linear thing, and if your new piece of data is bigger than your old piece, it will start to overwrite the next thing that was on the tape. And if your new piece of data was smaller than the original piece of data, there'll be a bit of spurious data at the end, right? So the physical characteristics of these storage devices affected the way that data was stored and used. So, because of these problems, they started to think of a different way of representing data, and they had this idea of a navigational model, right? There's different types of navigational models, but essentially they're a bit like the way that memory is referenced in the computer. You have, rather than blocks of memory where each thing is stored, your program will reference blocks of memory that is the variables we think, but those variables will point to different blocks of memory where an arbitrary size block stores the information. So in the same way, the databases evolved to use this so that you could more easily rewrite things. Still some constraints though because of the physical storage characteristics. It was only when they started to move to hard disks and other types of things like that, which had more flexible storage characteristics, that databases truly came into themselves. which happened in the early 1970s. Okay, there were still a lot of punch cards used in the early 1970s. Most people who learned to program in those days just still used punch cards right up until the 80s. But in industry, basically they talked about this idea of relational data. Okay, and this is what modern databases are based upon. And it's based around logical representations of the data, where we have tables representing things, where one item in the table, usually sometimes multiple items, are the keys to the data, and you use that to look up the related information to that data. So you might have, for a student database, the key will be your student number, and then from that student number you can get your address, your results, your study department, your degree program, all that information that's related to your student number. There's been some work on more sort of object-oriented type databases and object relational mapping and that sort of thing. I'm not going to spend time on that because the main...
I'm just doing a quick room count. It won't be a sec, sorry.
So the main type of database systems still in use these days are the ones based around structured query language, or SQL. There's lots of different versions of it. Oracle do the biggest commercial one, right? But you'll see lots of alternatives to that, including free ones like MySQL and NoSQL and that sort of thing. They all have essentially the same representation and the same type of queries. So if you learn to use structured query language, you might see relatively small differences when you use a particular flavour of it, but it's relatively simple to do. Okay, so let's talk a bit more about storage issues. First of all, you have programs in memory. Okay, when you're running a computer, you're storing your information in the computer memory. And we're generally talking about object-oriented programming these days. So we have rich data types. So every object has a fair amount of information attached to it. In the same way that I said, you know, the student number accesses all these things. If we have an object to represent a student, there's a lot of information stored in that object. And it might be references to other objects, or it might just be straight data fields, like a string for your address, that type of thing. But there's a lot of information stored about every student, and every staff member in the university, and every room in the university, and, you know, all sorts of things have lots of information stored with them. And essentially that data structure is some sort of connected graph, where it's connecting all those different objects together in some sort of way. And sometimes it's not just like a tree-like structure. Sometimes you get loops in it, things like that. So it can be quite complicated, the way that that data is represented in memory. Furthermore, it can change dynamically. Okay, so if you as a student enroll in a new module within your degree program, say you take a language module on top of your regular ones, then that gets added to the list of modules that you have. So it's changing. And the navigation is by object reference. Okay, so I talked about the idea of looking up a student by student number, but when we're storing it in memory, we're not doing it that way. We're just having a direct reference to a particular student or that sort of thing, right? We might have a way of searching by student number or something like that still, but we are referring to particular objects. Memory pointers is the way that they're stored. In contrast, the database files are on disk. Okay, and when we're talking about databases, we generally are talking about old mechanical disks because they are still used more frequently than solid-state devices for large data volume. Right? It is shifting, okay, and there are differences in the way that data is stored on an SSD, such as what you would have in your laptop, and a mechanical hard drive, such as you would have on a mainframe computer, but still the majority of it is on a mechanical disk. Okay, and in your database files on disk, we're using relatively simply typed data compared to the complex objects that we store in memory. And we're using a fixed, predefined set of tables. Okay, so always we need to define when we start developing the system what that set of tables is. They've got a fixed width, so how many columns you can have in the table is fixed. You can't change them arbitrarily because you want to add new fields to your object. Okay? What you can do instead is add new tables. Okay, so you can't change an existing table because your existing tables in there are going to have a lot of data in them already, fully populated. If you added another column to it, then that column would be empty for all of the things that came before. And that's not a good thing in a database. Okay, you can sometimes have empty fields within a database, but generally having a large number of rows within your database with empty fields is a bad thing. So you can't grow the width, but you can grow the number of rows. So you can add extra items into your database. No problem with that. Just not the columns within your things. And as I said, the navigation is by searching according to key values. Now your key value can be a single item like a student number, or it could be a combination in some cases of different columns within your things. So you need something that's unique in order to access something, but you might have some way of creating a key from the combination of different columns. I'll talk more about that in a bit. So first of all, relational databases. The original purpose of relational databases was to eliminate the redundancy of stored information. Okay, so don't store the same information in several places, and eliminate blank fields and repeated groups of fields. We also want to minimize the dependency between data items. That makes it easier to search for data, easier to insert, update and delete things in the database, and gives you fewer cascading effects. It's going to be easier to understand these when I come to some examples in a bit. Right? So in a relational database, essentially the structure is a set of tables indexed by row and column. In terms of the physical storage of it, it's essentially a set of files containing fixed length records. They're fixed length because we know exactly how many columns there are for each record, and we can define a fixed amount of memory for each of those columns. Okay. So here's a couple of examples of database tables. The current account table here is indexed by the number, the account number, that's why it's underlined. And it has two fields of a balance and an overdraft limit. Right? You might have more things associated with the current account, but in the simplest case, let's just look at those two. Here we've got the holder table with the customer ID being the key. Okay, it's just a number. Forename, surname, and an address ID. Okay. Now, the table columns represent attributes. They should be simple types. So, a string or a date is probably about as complex as it gets. They're not going to be detailed objects. And each of these types has a fixed size. So some of you will have well, maybe some of you will have come across the situation where there is a fixed width for names. Okay? And sometimes we get students who have very long names who find that for particular databases, their name gets truncated. Right? So, you know, they choose an arbitrary number of characters that you can have as a maximum size for the name, maybe 20 characters or something like that. And people, particularly of Asian background, Indian, Sri Lankan, that sort of area, who have very long names sometimes, fall foul of this on a regular basis. Okay? Also, sometimes they restrict the types of special characters that you can have there. So sometimes people of European descent who have umlauts in their name or cedillas or that type of, you know, special characters find that they can't use them when they enter their name because they're restricted to just an ANSI character set rather than the full ISO character set. So it can be frustrating for those people whose names aren't represented properly. And it's a consequence of the database design that happens. But you do need to choose a fixed size because of the way the database is constructed. Every column needs to be a fixed size. Okay? In contrast, the rows represent objects and they have mixed types. Okay, so here we've got an integer, then two strings, and then this address ID thing, which I'll get to in a bit. This will be a reference to another table. Right? Why would you have address ID referencing another table rather than just storing the address in the table there?
Because the other table has some information that we need to get into our table.
Yeah, but why not just put it in this table? So every customer is going to have an address.
To eliminate the redundant information.
Okay, so why would putting the address in there have redundant information? It's the right answer.
Yeah, because it says already started there.
So yeah, so essentially you might have 4 or 5 people living at the same address who have accounts with you. And so you can just store that one address for those people. And but it does mean that you need to keep track of, make sure that when the address gets updated for one customer, does that affect everybody at that address? Or does it mean that's a new address for that one person kind of thing, right? So, you know, it does create problems in itself. You need to think carefully about the consequences of it. Okay, to make that clear, say we had an address that rather than having a street number, had a named house, right? So, as is common in rural areas around here, there aren't street numbers. The houses are called something like Dale Cottage or something like that. And say the householders at that address decided to change the name of their house to House and Cottage, for example, instead of Dale Cottage. So that should affect everybody living at that address, right? But if a customer came in and said, my address is exactly the same, it's just I'm at House and Cottage now, does that mean that they changed the name of their house, or does it mean that they moved into the house next door, which would still have all other characteristics of the address the same, would have the same postcode and that sort of thing, but you know, it's not going to affect the people who stayed in the old house. So those sorts of things are things that you need to consider about when you're updating an address. Is it going to affect everybody at the address, or is it going to affect the person? Does it mean the person's moved house? Okay. database profile. So if we're talking about a UML representation for a database, it's similar to a class diagram, okay? But what we do is we put this table at the top here to indicate that it is a data table, right? So this is the name of the table holder. And then down here, we've got the columns within the table, specifying the type and, in the case of strings, the length of the string. We haven't specified the length of this string here because it's a special type of string. I'll come back to it. This one at the top, the customer ID, which is an integer, has been labelled PK. PK means this is the primary key. This is the thing we use to look things up. Down here, where we've got FK, this is foreign key. And essentially what that means is this is what we use to look up that information in another table. And the reason that we didn't need to specify the size of a string here is that that is a generated key, and so it's always going to be a fixed length anyway, right? This particular use of UML, as I said, it's not a golden standard of UML, but it's fairly commonly used, right? So if you present this to people who work with databases, they will understand what you mean. Okay, so primary keys. Here's an example where we've got a simple key, where the single item, the account number, is the primary key. Here is an example similar to the one on the previous slide, except that we've eliminated that customer ID, and instead we're creating a primary key combined with the forename and the surname of the customer. Now the thing about a key is that you need to have a unique key for every row in your table. So what's the problem with this second table? Yeah?
Maybe two people have the same name.
Yes, exactly. Two people with the same name. When I was at school, there were 3 boys in my class called David Smith. Okay? And those of you of Chinese background probably have come across examples of Chinese students who have the same name. Very commonly shared names. I don't know if there are examples in other language groups. Yeah? Yeah, there are. In fact, I know actually I've had students called, I had one class with 2 students called Muhammad Ibrahim. Okay, and I'm sure that many of you, whichever ethnic background you come from, you have examples where people have the same name. So that's why in the previous example we had a customer ID as the primary key, as an extra column within this table for the account holder. Right? It isn't enough to just base it on the forename and the surname. But just going into that in a bit more detail, this is the idea of a generated key, where you have multiple columns within the table that are put together to create a primary key. Rather than doing that, it's recommended to use a generated key if no other suitable key can be found. Okay, so if there is no way from the data within the table of finding something unique, or if the compound key is too large, so if you had to have 6 different columns within the table in order to make up the compound key, it's It's just getting a bit complicated to have to enter all that information every time when you want to search for a particular item within the thing. But you don't need to have a generated key for all tables. Sometimes there is something unique about a particular column within the table that will mean that you don't need a generated key, like a special person identifier or something like that. Sometimes the nature of the data provides its own key, right? So don't do a generated key for every table. Okay, so you couldn't use a driver license number as a primary key because not everybody has a driver's license. In fact, I'll bet you there are people in this room who don't have a UK driver's license, right? As I said before, forename and surname can't be a compound primary key because of duplicate names. So we create this generated key for customer ID. Every time a new customer gets added to the database, there's a counter which gets added, incremented by 1, and that's the new customer ID. Okay? And that gets associated with the person. Same like your student numbers, right? Okay, and we have the foreign key idea. Okay, so we have 2 tables here, one with the account holder, one with the address. You have every address in this table is essentially going to be unique, right? You shouldn't have duplicates in this table. Why not?
Well, because we connect people from other tables to the same address with address ID.
Yeah, so basically the idea of an address is it's a physical location. You can't have multiple physical locations that have the same address, right? They might have elements of it that are the same. So talking about named houses, there might be a house in one village with a particular name and a house in the next village with a particular name, but it's only the house name that is the same. The other information in the address is different, right? So, in a sense, every row in this table, even if you didn't have this primary key, should be a unique item. But you probably need to refer to every field, every column within the table in order to make up the compound key that would represent that unique address. And that makes it very difficult to put in a reference from another table through to there if you have to specify everything within it, right? So that's why in this case, we create this arbitrary key every time an address is added. And rather than putting in the full reference to the address in this table, we just use that short string to make the reference. Okay, sorry. Animations on these slides are not working properly. Okay, so this is FK standing for foreign key. So the value of the foreign key in this table is the same as the value of the primary key in the table that it's referring to. Okay, so you might have an instance where your foreign key is null. Okay, so say you didn't have a valid address for an account holder. Say they moved address and they didn't tell you when the mail was sent back saying not known at this address. Then you could delete the reference and have it as null. Could be possible. But if it's not null, then you have to have the row with that primary key in the address table. Okay. moving around our databases. The tables are linked in one direction only. Okay? So they link from the many to the one side. Why? What does it mean to have a linked table like this? So we've got many book copies, one book title. So this is part of a database associated with the lending library here.
Maybe because each book have a unique title.
Yeah. So in the same way, on the previous slide, here, again, we had the many to one, right? We've got the unique addresses here, potentially being associated with many householders. Okay? So in the library, we might have 10 copies of Somerville. Okay? But this information about the name and the author is the same for every single one of those 10 copies. We have a primary key representing the book itself. It's given as a Dewey ID, which I don't think is the appropriate name for that field, because any book of the same title should have the same Dewey reference number. People know what the Dewey reference number is?
Something related to referencing book.
Yeah, so when you go into the non-fiction section in the library, all the books on the spine have a number like 391.567, and then the first 3 letters of the author's surname usually is the way that they're done. All of the copies of the same book will have the same reference number on the spine. But still, presumably they're generating some primary key based upon that number and perhaps a counter for the number of items there are or something like that. So it'll be a generated key as well, probably. Okay, and then it's got a Boolean field to indicate whether that copy is on loan or not. It's using the ISBN in both cases. Now the ISBN is a unique number representing a particular edition of a particular book. Okay, so if you look at any physical book, in the title page there will be a bit, or sometimes on the back cover of the book, or sometimes both, specifying the ISBN. There are 2 forms of it, there's a 13 and a 10-digit number, but both of them are unique. Yeah. So it's a good way of referencing it. Now, data normalization. Sorry. I did not mean to have animation in here. Right. So, the idea of data normalization is it's a way of transforming data tables into what's known as normal form. And it's essentially about the relationships between the different data fields within the table. There's lots of different forms of normal form. First normal form, second normal form, third normal form, fourth normal form, fifth, and even sixth. Really, I don't know. Some people say fourth normal form is desirable. Generally, third normal form, or something known as voice cod normal form, are the best forms for your data tables. And I'll talk in more detail about what these different normal forms are, okay, because this is the key part of what we're covering today. We use this idea of entity relationship modeling as a method for doing normalization. So it's about understanding the relationships between the different bits of data. And it's you wanting to simplify the object relationships and multiplicities. And generally it will always achieve third normal form, which is pretty well as good as you need, and sometimes does better than that. Event-driven design is a new idea which comes about in part from one of the lecturers within our department, Anthony Simons, which is looking at a different technique for achieving the same sort of thing. And it constructs a data model which is already in third normal form and sometimes better than it. Okay, so it's just a different approach for achieving the same results. Okay, so let's talk first about the types of relationships that you can have in databases. The most simple, of course, is one-to-one. Every student has a U card, and every student should have only one U card. Right? Each bank branch has a unique address. Okay, bank can have multiple branches, but any branch has to have a unique address. A one-to-many relationship is something like an address contains many householders, or can contain many householders, one or more. A person optionally has a driving license, so that's a 0 or 1 relationship. A woman optionally has many children, so that's 0 to however many. A person optionally may also be a student. Or a person optionally may also be a staff member. We're talking about an institution. And then we have many-to-many relationships. So many modules are offered on many degrees. So some of your other modules, you have students from other MSc programs studying with you. Right? But this module, it's only the SSIT students. Books are loaned optionally to a borrower. So a book can be on loan or not, and borrowers can have 0 or many books out. Another one, borrowers optionally can reserve books. So this is borrowers from 0 to however many, and this is books from 0 to however many. So any given borrower can have however many books reserved, maybe none, maybe 20, doesn't really matter. And any given book can be reserved by maybe no one, or maybe 30 people. Right? So that's a many-to-many relationship. Now, when we're designing databases, one of the things we want to do is to minimize data dependency. So we want to remove duplicated data. So when we update the information in one place, we don't want to have to update the information in another place. Because if that happens, there's always a risk that the data will get out of sync. So we should have, for any piece of information, we should have a single instance of it, and anything that needs that piece of information should refer to it rather than duplicating it. We also want to remove redundant paths, because the more paths to data that we have, the way that data is linked, the more memory we're going to have to use up in terms of storing it. Okay, so it's not as critical as removing the duplicated data, but it's still a design aim. We want to optimize the table structure for the independent insertion, update, and deletion of single data items, reducing cascading effects. And I'll talk more about that in a bit. So, minimization technique. First of all, merge tables that are in one-to-one relationships. This minimizes the need for a join. So if I have every student has a unique U card, and every student has a unique student ID number, which is not the number that's on your U card but a different number, don't store them in 2 separate tables, put them in the one table. Right? So because that means if I want to get both of those pieces of information, I don't have to do a join, which is basically getting information from two different tables. And we also want to link tables that are in a one-to-many relationship. Okay, so if I have things that refer to like the book instance, so I have one book and I have information about whether it's on loan or not. I also have information about who's reserved it, right? And they're probably stored in different tables, okay? And so what I do is I link those tables. And we introduce new linker tables to encapsulate these many-to-many relationships, sorry. Okay, so many-to-many relationships are really hard. Virtually impossible to encapsulate in a single table because you can have more, you know, there's no unique key, or you can have multiple sort of duplicate items if you do have unique keys. But if we have linker tables, then it reduces the amount of information we have to store in any given table. We also find redundant search paths by navigating to the same sets of rows and deleting the shorter path. And again, this will be, I think, easier to see when we do look at some examples. So let's look at some examples. First of all, here's an example of where a merge is required. Okay, we have a student linking to the person table, linking to the degree table, and linking to the UCard table. This is a one-to-one relationship. There's a unique UCard for every student. So we don't need to keep that separate, okay? You can't have a UCard that exists independently of a student, and you can't have a student that exists independently of a UCard. Sorry, that sounds really awful, but it's true. You have to have a UCard. Even if your UCard has been destroyed, conceptually you have a UCard, right? So we simply take that information from one table and put it into the other. Which table do we move into the other? How do we decide which table disappears? Well, generally we keep the stronger concept. In this case, the student is the stronger concept, and so it subsumes the UCard. Okay, it would be very strange to do it the other way around and to put the information from the student into the UCard table and make that the top level thing. Yes?
Why do you create the UCard table in the first place? Why do you just merge them at the beginning?
That's a very good question. Okay, so so the question was, why was the UCard table even created in the first place? And it might be because the student table already existed and somebody introduced this idea of UCards, so they were a new concept, and they said, well, we need to keep a list of all the UCards, so I'll create a table full of UCards. And they weren't thinking of the whole database as a concept, they just were thinking about this thing that this concept they were dealing with. So they were creating the physical UCards, and they weren't particularly thinking of every one of them was going to be associated with an individual student. They were just keeping track of individual UCards and not thinking of them in terms of something associated with the student. You're right, in this particular instance, it was a bit silly for that table to even exist in the first place, but you will see instances where that sort of thing conceptually happens. Perhaps a more common type of thing is where people started off with something that had really grand plans, and they were going to be multiply associated, have something that had multiple associations in the first place, but then the project got scaled back, and so it ended up being a one-to-one relationship where originally it hadn't been planned that way, right? And so in that case, recognizing that you can simplify the database by doing a merge is a useful thing. Okay. Again here, we have two potential primary keys, because in the UCard database, the card number was a primary key. And in the student database, the registration number was the primary key. Okay, I don't know why they have different numbers for the UCard and the student registration number, but they do. Okay, again, this is something strange, which does exist. So in a sense, it's kind of arbitrary which one you decide to use as your primary key for this table. Okay, you could use either of them. Given that you had already lots of references out of this table to student, which was probably already using it as the primary key, and you didn't have anything referring into the UCard one, it makes sense to use the registration number, which was the one that was used in this table. But, as I said, to a certain extent, it's arbitrary. Okay, here's an example of the part of the library system, right? So we've got book title with multiple book copies. We have a loan, which has the date that it goes out on loan and the date that it needs to come back, which is going to depend upon the type of loan that it is and that sort of thing. Each book copy is associated with a particular borrower, and each borrower is associated with a number of book copies. Right? So for any user of the library, they can have however many books out on loan, which might be 0 or it might be whatever their loan limit is. In this case, their loan limit is 6, because it says 0 to 6. Right? The book, there's only one instance of a book, so it can either be borrowed or not. So that's why it's 0 or 1. And the householder itself has to have an address, the borrower has to have an address associated with it and other information too, probably. Right, so we've got up here an end-to-end relationship. And that's an awkward thing with databases. We want to get rid of end-to-end relationships. Down here, we've got one-to-end relationships. They're fine. So it just means multiple rows in a table. Okay, so how do we get rid of it? Well, we shift that loan to be, rather than branching off, to be in the middle. So for any particular loan, there's going to be a book associated with it. And for any particular book, it's either on loan or not. Okay? And also, for any particular loan, there's going to be a borrower associated with it. And for any borrower, they can have up to 6 loans. Right? So now, we've got one-to-many relationship here, and a one-to-many relationship here. We've got rid of that M-to-N relationship that existed between these two here, which makes it much easier to represent things. Okay, so the association occurs in this linker table here. And the linker has exactly one of each object in it. Okay? So for every loan, there is one book and one borrower. Okay? Within this loan table, there might be multiple instances of the same book, presumably each one with a separate borrower. There might be an instance where one borrower wants to borrow 5 copies of the same book, but it would be strange. Now the problem here is, if we have one borrower get 5 copies of the same book, then as it was on the previous slide, we had no way of generating a unique key for that loan, because the loan fields were essentially just the book copy and the borrower, the issue date and the due date. Right? But the book copy is the copy of the book title. Right, so we still get, if we use these two things together, we will have a unique key. Because remember, the book copy, the Dewey idea of the book copy, referred to that physical edition of the book. As in that particular printed copy, even if there were 5 copies of the same edition of the book, we're talking about this physical copy versus that physical copy versus that physical copy, which might have all exactly the same except for that unique number identifying them. Okay, so we do, between these two fields, generate a unique key. Yes?
But doesn't it mean, for example, if I borrow one book today and borrow the same book 2 days after today, it will have the same member ID and the same book ID, no?
Yes, but the reason that we're using this table is so that we can look up the issue date and the due date. So if you borrow this book today,
Yeah.
in order to borrow it in 2 days' time, you have to return it, so it would be removed from this table, right?
Yeah.
And then you would get a new one in for your next borrowing instance. Okay, because you can't borrow a book that's already borrowed. Sometimes, I have had situations where I've gone to borrow a book from the library and I've gone to check it out, and it's appeared, the system flags it and says this book is on loan, and then they have to return it for the previous person who, for some reason, when they returned it, it didn't get through the system properly, and they were probably accruing fines because it's been on the shelf all that time, but you know, that sort of thing happens. Okay, but that's kind of outside the tables, that's at a higher level of control.